I am so excited to go over slope fields with you. They look really funky, but they're actually very, very easy to make, and I hope just as easy to understand. Let's dive. So what are slope fields? What do they show? They're approximations of the graphs of solutions to differential equations. They're made up of basically lots of little tiny tangent lines. So it's almost like if you've ever seen like a wind field or a magnetic field, and if you've never seen either of those, you can be like, I have no idea what you're talking about. I like to think of them as like little conveyor belts or little mini tangent lines at points on the solution to a differential equation. And they kind of tell you all the slopes of that solution, right? So like, let's say that you have the derivative of something is, let's say like, I don't know, x to 3x squared, right? Then all of the slopes of x cubed plus c, that would be the solution of this, right? When you take the integral of it. All of the slopes of this thing would be on the slope field. And all of the slopes are described by this equation. That's it. All right, so now that you've got an idea of what one looks like, and you're probably thoroughly scared of how the heck do I create those, let's see how easy it is. So we're gonna do 3 of them in this video. Here we go. Sketch a slope field for the differential equation dy dx equals 2x. Sketch a potential solution curve through the point 1, 1. So we're going to talk about that. We're not going to go and solve out these differential equations. We're just going to draw in slope fields. So how do we do that? Now, we're not going to plot every single dot on this curve. We're going to just plot a few of them, right? So it's going to be up to your teacher how many points to plot out, because there's a lot on here. But essentially what we do is we literally just take x values, plug them in, and what will come out of dy dx are the slopes at those x values. So very simply, I'm going to either set up a table or just be nice and organized. So I've got a table of values right here. And here the slopes only depend on my x value. So I'm going to plug in, let's start with like x values at, I don't know, -2. If I plug in -2 into here, dy dx is equal to 2 times that x value, right? 2 times whatever that x value is. So it's going to be dy dx equals 2x. So literally, that's just calculated by doing 2 times -2, which is -4. So what does that mean? That means any point of x equals -2 has a slope of -4. So you just rough sketch that. So here are all the points where x equals -2. So that would be a slope of -4. I don't know. It's just something like really, really steep. And your teacher's not going to make you like get out a ruler and like a protractor and make it perfect. But everywhere x equals -2, you're going to get the same slope of -4. Just estimate it. Just got to look negative and relatively steep. If you're doing it on the AB or BC exam, that's the case as well. All right, so we're going to plug in -1. So I plug in -1 into the slope function. That's 2 times -1. So all the slopes at x equals -1 are -2. So that's a little bit less steep, something like that. And again, these are not going to be perfect drawings. Just needs to be a little bit less steep than what we just have. And all the same slope, because all along x equals -1, we get the same slope. At 0, that's an easy one. 2 times 0 is 0. What that means is all of the slopes on the function that came before this, on y, is 0, right? Just like before, the tangent line slopes would be 0 at every x value equals 0. So you put in little mini slopes that look like that, slopes of 0, just like that. Not so bad. And that gives you an idea of the slope field. We'll go with 1. So 2 times 1 is equal to 2. So all the slopes are 2, so that's +2. So that's going to be roughly like that. And again, just have rough slopes there. Mine are not going to be perfect. They should be roughly the same right at those points, like so. And then my final slope at 2, I plug in 2. So it's 2 times 2 is equal to 4. And that gives me a steeper slope. So I just want to make sure that these lines are steeper than the last ones that I just drew. Just kind of draw them in there like that. And we're good. Now in this slope field, all of the slopes were just with respect to x, meaning we didn't have to plug in y values, which we'll have to do down the road. So what we have right here, we've got our slope field. Now it says, can we sketch a potential solution curve through the point 1, 1? Here's what you do for that. You put the point at 1, 1. We're being told, yes, the solution to this goes through the point 1, 1. And then you just kind of use these as conveyor belts. We see that here the slope is kind of like that. And then as we move on to the right, our slopes are going to get steeper. You don't actually have to touch any of the other slopes. But as we get closer here, it looks like our slopes are going to get less until they zero out right there. And then they get steeper up like this, steeper and steeper and steeper, which makes sense because the solution to that differential equation, right, is roughly the graph of x squared. It wasn't a perfect graph by any means, but it's roughly a graph of x squared. Isn't that cool? I think it's pretty gnarly. Okay, so we're going to do one more in this video, and this one's going to be completely with respect to y. Then I'll make a final video on slope fields where we have to do it in terms of x and y. And again, I'm not going to do every single point on this slope field. Not bad though. Let's plug and chug. Here we see the derivative is equal to y. Only y, which means when we learn to solve this, and we will in the not too distant future, we'll see that the function, whatever that function is when we solve this out, will have slopes that are going to be on the slope field. All right, so we got a table of values, and you don't have to write down a table. I just like doing it. The y values are what we're choosing now. Notice that it's just the y values that determine the slopes here. So what are some good y values? Well, we'll do -2, -1, 0, 1, and 2. So okay, so when we have a y value of -2, it's very easy. dy dx is equal to y. The slope is the same as that y value. So we're going to now draw slopes that have -2, but that's all along y equals -2. Because every point along this line has a y value of -2. So that's a slope of -2. So I don't know, something pretty steep like that. And it just has to be the same slope. Very neat that we see that all the slopes along the y value are the same. And that's because this is only in terms of y. Okay, -1. We plug that in. It's easy to calculate. The slope's -1. So all along y equals -1, we'll have slopes of -1. Not as steep, but still negative as the last slope that we just found. And to find this, I kind of line it up here to go like down one, right one, roughly. But it's not perfect, as you can see. Now, from here, what are the slopes at 0? Well, let's just plug it in. The slopes along y equals 0 are 0. So there we have it. Just got little tangent lines to draw on there with a slope of 0. Sweetness. Beautiful, right? Then, what about 1? Well, if I plug in 1, the slope is 1, so that's now +1. It's an interesting looking curve. Very, very cool. Like so. Just drawing in slopes of 1. And they got to be positive. And then 2 plugged into that is going to be a slope of 2. So that's going to be steeper. And again, these are not perfect slopes, but it gives you an idea of what the curve is doing. Very, very neat. Okay, so now what do we do to sketch out a solution curve if f of 0 is 1? Well, again, I'm going to plug in 0, 1. That is a point that is definitely on the solution curve. This represents all the possible curves that could go through this. But because we're up here, it looks like the slopes are getting steeper as we go over. And again, it doesn't have to go through any one point except for that point where the solution is, and then it's going to come down. But as we get down along here, we're not going to cross the x-axis because all the slopes as we go to the left zero out. You get a horizontal asymptote. Kind of looks like an exponential function, right? So my guess is it's something of the form a to the x, something like that, which is very, very rad. Okay, what I'm going to do in the next video is I'm going to show you how to go over a slope field when we have both an x and a y value involved. Super easy to do and pretty cool. That's it for slope fields. See you in the second video on them. Peace.